So question 3 is essentially the opposite of question 2. Question 2 requires awareness of what dTOR and dt actually mean, i.e. they're the intervals between ticks of a clock, and that requires some thinking about to get your head around. But once you understand those concepts, you can get the right answer. Question 3 is just algebra. It's making a transition between two coordinate systems. It's something we did in the homeworks, and it's something we did in class several times. So if you have trouble with the conceptual side of general relativity, this kind of question should suit you. So let me put up the algebra for part 3a and talk through it.
You write down the equations for x, y, and z in terms of the angles phi and beta, and then you write down the expression for a general vector r, but you replace the expressions for x, y, and z with the ones you just wrote down in terms of phi and beta. Once you've done that, you differentiate the vector r with respect to the two new coordinates, phi and beta. And each of those differentials yields an expression for the basis vectors e phi and e beta in terms of ex, ey, and ez. You can then go on and use these expressions to generate the metric coefficients. So we'll do that next. So once you get done making the expressions for all the basis vectors, the next bit is that you take all the dot products between the basis vectors, and those dot products give you the coefficients of the metric tensor. And of course, the off-diagonal components are all symmetric, so g beta phi is the same thing as g phi beta. So if you've got a 2 by 2 metric corresponding to a two-dimensional space, you only have to calculate 3 independent metric coefficients, and the fourth one is equal to the other off-diagonal component. By the way, I'm now away from the airport. I got to where I'm going, so there will be less background noise in the rest of this revision lecture, which I'm sure will make you all very happy. So this is just the mathematics of calculating the 3 independent metric coefficients. I guess you can just hit pause if you need the details of this maths. The off-diagonal component is 0. So the next bit of the problem, you write down the general expression for a Lagrangian as the square root of gij times dxi by dl times dxj by dl. There's no minus sign, and the parameter is just the length along the path corresponding to the physical trajectory followed by the body. We're not in a relativistic scenario here, so we don't have a fourth component corresponding to time. We don't need the proper time parameter or any of that heavy lifting stuff. So this is the maths you use to form the Lagrangian out of the metric coefficient and the coordinates. So in the next bit of the problem, you find a cyclic coordinate. If you remember, to identify cyclic coordinates, you inspect the Lagrangian, and the cyclic coordinates are the ones which only appear as derivatives with respect to the parameter. So in this case, we observe that phi is a cyclic coordinate, and to find the conserved quantity, what we do is we differentiate the Lagrangian with respect to d phi by dl, and that yields the quantity shown in the algebra, which you can see here. So we next go on and find the Euler-Lagrange equation in the other coordinate beta. The Euler-Lagrange equation in phi can be expressed as the conserved quantity, which I've written as capital C in the algebra you just saw, as being a conserved quantity. So that conserved quantity statement is essentially the other Euler-Lagrange equation for the parameter phi. So here we're just taking the partial derivative of L with respect to d beta by dl, which gives you an a squared d beta by a dl, and the partial derivative of L with respect to beta, which gives you a more complicated function of beta and d phi by dl. And so putting them together, you get an Euler-Lagrange equation which is second order in beta, but which also contains a d phi by dl squared. You then substitute in to remove the d phi by dl squared and express that part of the equation in terms of the quantity c, the conserved quantity, and that gives you the equation at the bottom of this page, which is a second order partial differential equation for beta in terms of L. Now in general, second order equations are not that easy to solve, but I taught you in the course that the second order equations you typically encounter in general relativity can usually be reduced to first order equations using a trick substitution. This works because the equations from Lagrange's formalism in relativity are very rarely a function explicitly of the actual parameter L in this case. So as long as that a parameter doesn't appear explicitly in the equations, you can reduce them to first order using the following substitution. The substitution is letting u equal to beta by dl, which means that du by dl, which is the same thing as d2 beta by dl squared, and also is the same thing as u times du by d beta, can be substituted into the equation. So the left-hand side, instead of being d2 beta by dl squared, becomes u du by d beta, so the equation can be re-expressed in terms of u and beta with all of the l's absent. I guess one of the harder bits of this problem is recognizing by inspection that this integral can just be done. The sign that it can just be done is the sign beta in the numerator and the factor of something plus something times cos beta in the denominator raised to a power. So it is integrable by just reducing the power of the denominator, because the numerator will appear by differentiation when you differentiate that new denominator. The final bit of the question is taking some special cases. The most general solution for paths on the surface of the torus is actually very difficult to solve for because you have to integrate the equation you just derived again. But by setting some of the constants which have appeared as integration constants to 0, you can get some physical intuition to the meaning of the solutions in those cases. If you set c equals to 0, the conserved quantity equation turns into d phi by dl equals 0, which means the azimuth angle phi is fixed, so your trajectory must be a point that moves around the small circle of the donut. This means in the other equation that beta equals L times the square root of d. So that constant d that appeared, its square root must be equal to a, the radius of the small circumference, and so that equation becomes L equals a times beta. So that gives you then a modified equation for d beta by dl. For the other special case, you set c equal to r plus a cos beta. So then d beta by dl is 0, which means that your point isn't moving around the small circle at all. And in the other equation, you get d alpha by dl equals 1 over r plus a cos beta, which can be solved to give L equals r plus a cos beta times alpha. So there we're talking again about circular orbits, but this time the point is moving around at a fixed beta around the torus. So it's making circular orbits around the large circle of the donut. So both the small circles and the large circles are geodesics on the torus. They correspond to as close as you can get to straight lines in toroidal geometry. The intermediate cases where you have something that spirals, wrapping itself around the torus whilst going around it, the donut at the same time, will have c taking an intermediate value between 0 and the maximum, which is r plus a cos beta. That's the end of question 3. It's a much more mathematical question than question 2. On the other hand, it doesn't really require so much in the way of thinking about the meaning of the concepts, and so in many ways it's actually an easier problem. On the other hand, it's probably the hardest problem in this particular exam paper, so most students in the exam when they took it in anger actually avoided this question.